Thanks. So let me introduce the next speaker, Laercio Pilla. He's from Federal University of Rio Grande do Sul in Brazil. This talk he will present. This actually is a submitted paper talk. He will present some work he did for combining the energy saving and the load balancing in CHARM++.
Thank you. Can you hear me? Is it loud and clear? Okay. Bit louder? Okay. So, good morning, everyone. And my name is Laercio Pilla. And the work that I'm going to present today is actually the work of Edson Paduin, but he could not come here today. But since me and some other people have been working with him on that, I'll be presenting his work. And this work is developed in a cooperation between the Federal University of Rio Grande do Sul in Brazil and the University of Grenoble in France. Okay. And I'll try to explain what do we mean by saving energy by exploiting residual imbalance on iterative applications. And to start, okay. Okay, okay. Okay, and to start motivating this work, I do not have to explain to you the problems that we are facing with energy consumption and power consumption on parallel platforms, and what do we need for the future, and we are still far from it. But the thing is, considering energy and power consumption, when we are thinking about load balancing, it may happen that we have a load imbalanced application running, and if we just check the power consumption in the different sockets that we have there in the parallel machine, we may not see that there is a difference in the power consumption between them. So what does it mean? It means that we have an imbalanced application that we know that's running there, but the imbalance and the idle times that we have there are not changing the power consumption that we have in that socket, which means that we are not doing any actual work, but we are still consuming power there. And to try to work with a load imbalanced application, we usually do load balancing, but there may still remain some load imbalance when we're doing that kind of thing. And to work on that residual imbalance, we are going to do some things that I'm going to explain later. So just the thing here is that we have several sockets that are running our imbalanced application, and we see a constant power demand. In the figure, we have the power for each socket in the vertical axis. And this ends up resulting in similar energy consumption for the different sockets. And we know that we are wasting energy in this case. So the goal of our work is to try to reduce the energy and power consumption that we have on a parallel machine, and when we are working with some imbalanced application. And we are going to consider the workload that we have on the different cores and different sockets. And the main idea here is that we want to provide the same performance or a better performance while using less power, okay? And what he's proposing in this work is a combination of dynamic load balancing with dynamic voltage and frequency scaling. So, and for that we have some tools that have been developed. Having explained our motivation, I'm going to discuss these two tools, these two components that we use, the energy daemon and the energy load balancer, let's say. And I'm going to discuss some initial experiments with two different prototypes of energy LB. And then I'll go to the concluding remarks, okay? And these two components that we use, we have this energy daemon that is going to be responsible for getting to know on which machine you're running and getting information about power and energy consumption. And this may vary from platform to platform because we may have some model-specific registers that are going to tell us what is the energy that we have in the, being consumed by a socket, or maybe the power. And when we get one, we can compute the other if we do that periodically. And this energy daemon, it's currently working on Intel and ARM processors like big. LITTLE processors. And it's also going to trace the execution of the application here. So we get our application running, and we know afterwards where were the peaks of power there and the kind of figure that I presented earlier, okay? And besides this energy daemon, this tool, we have a energy LB that is a Charm++ module. And I'm not going to explain anything about Charm++ to you today because I imagine that you know a lot of it. But the important thing for us is the load balancing framework. And we build this module as a load balancer, and then we can use it together with the application, right? And this module is not as actually a load balancer because it's not migrating chars or tasks around. It's currently focusing on computing the residual imbalance that we have and controlling the clock frequency of the different sockets. So what do I mean by residual imbalance? Is that I have a core that's going to be the most loaded one, and this one has to run at the highest frequency possible. But the other ones that have less load, they can run at a smaller frequency and try to complete their execution at the same time. And with that, we're saving power, okay? And we have two prototypes working right now for energy LB. So there's the centralized version that to do this kind of load balancing plus frequency scaling, we attach it to another load balancing algorithm. So we're going to have a main load balancer and that working with it, okay? And the main limitation of this version is that it's going to use only one core per socket because these were the first experiments that we had, and we cannot control the frequency of the different cores inside one socket. We can set what actually happens is that we set the frequency for the whole socket there. And to work with all cores in the socket, then we're going to use the hierarchical version here. And this hierarchical version is like a hierarchical load balancer, where for each socket we have a load balancer that's really going to migrate tasks between the cores inside that socket. And this is organized as a tree. So we have this root load balancer that's going to be our energy LB module that is going to see the differences in load between the sockets, and it's going to set their different frequencies, okay? And then inside each socket we have a load balancer that's going to migrate tasks, okay? And again, these versions of this module are not migrating tasks. The load balancers that are used with it are migrating tasks, okay? And for the experiments that we did with this module, we used an STI UV2000 machine that has 24 sockets. These are Sandy Bridge sockets, if I'm not wrong. And each socket has 8 cores for a total of 192 cores. This is a shared memory machine. Each socket is a NUMA node, okay? And the clock frequency that we have here can vary between 2.4 and 1.2 gigahertz. And again, dynamic voltage and frequency scaling is done by socket. And for the results, I'll discuss a bit about the first prototype and then the second one. And these are some results using LB test, is a benchmark that comes with Charm++, running 500 shards for 250 iterations. And what we have here in those figures are 4 figures. One when we're using no load balancer, and then greedy, refine LB, and just energy LB, just the energy module without load balancing, okay? The vertical axis represents the power for each of the 8 sockets used, and the horizontal axis is time. And what we see is that we know that this is imbalanced, okay? When we run the application with no load balancer, we have basically the same power consumption by the different sockets until the application ends and return to the idle state. When we use greedy LB or refine LB, we see that the execution time is going to decrease because we're doing load balancing and we are actually using the cores that we have there. So we're going to reduce the energy consumption of the application too by reducing its execution time. And when we are using just energy LB, what we see is that for the different sockets after the first 50 iterations, where we are going to gather information for load balancing, what we do is that we set the frequency of these different sockets for different frequencies, and we have different power consumptions for each of them. The total execution time is basically the same of using no load balancers, but we have a smaller power consumption and smaller energy consumption yet. And then we have some results with this, I'm going to call a POA bench. This is a benchmark that we developed that we can set some more parameters than LB tests. So we can add some things like more dynamic communication or dynamic loads, but we're not exactly using that right now, okay? What we have here are the results for the 24 sockets in the parallel machine and the total load that Charm sees in each of the sockets, because we're using one core in each socket, okay? What we see is that the execution time is going to be given by the slowest, most loaded socket here, the 24. And there's a lot of imbalance here, as you can see, all this white region here, okay? What happens when we use energy LB, we're going to set the frequency of these less loaded cores to a smaller frequency, and then the execution time is going to be similar for the different sockets. However, we are not able to fix this kind of problem here because we can only divide by half the frequency that we can set on these sockets. And here we have let's say a 10 times difference. So for this kind of scenarios, also load balancing is going to help us, okay? And what we can see here too is that this is going to be the energy consumption for the application for the different sockets when we are not using energy LB. And when we use energy LB, we're going to save this amount here of energy, okay? By reducing the power consumption, by reducing the frequency of the sockets. These are some results doing load balancing. What we have here is the total energy consumption for this benchmark using no load balancer in the first column, only the energy LB module, and then greedy com, refine, and refine com. And the red bars represent the energy consumption that we have with these different load balancers, but without using energy LB with them. And what we can see is that by just changing the frequency of these sockets or doing load balancing, we are able to save energy. However, if we use these load balancers together with energy LB, and so these are the 4 green bars here, we are able to save from 4 to 13% more energy, okay? Just working on these residual imbalance that we have in these sockets, okay? And we can see here is that in the red bars we have the total execution time, and in the green bars the total execution time when we're doing load balancing plus the energy module. And we're not changing the execution time when we're doing that, okay? So this is a very positive result for our initial results. For the second prototype, we did some experiments using Ondas 3D. So on this 3D is a real application, is a seismic wave simulator, where we have this three-dimensional region that is going to be decomposed as a 2D mesh, okay? And for ONS 3D, we have two sources of load imbalance. The first one is that the borders that we have around this region that we're going to simulate, they have some different computational loads because we have to compute the waves that are going to be absorbed there. And this takes from, let's say, 1.5 to 3 times more time to execute. And we also can have dynamic load imbalance because as the wave is propagated, we are going to change the load of the parts of the simulation that are going to be affected there. And this application was developed for different libraries, different parallel libraries and languages. And we just took the MPI version and migrated it to AMPI. Actually, another colleague of mine did that kind of work previously. And for this experiment, we are running 512 virtual processors on AMPI on the 192 cores that we have. So we have 3 virtual processors per core, if I'm not wrong. And what we have here, the results when we're using no load balancing algorithm, greedy LB, refine LB, or our second prototype using energy LB. And the leaf load balancer that is going to work inside a socket is going to be refined LB, okay? We have the average power, energy, and times that we measure for these different experiments. And what we see here is that when we focus on energy consumption here, is that when we're using greedy LB, in this scenario, we are going to increase the energy consumption of the application because greedy LB is actually increasing the total execution time. And that happens because migrating tasks in this platform can be very costly, and greedy LB is going to migrate them a lot, okay? And refine LB is able to save around 12% the energy when compared to no load balancing algorithm. But when we do our when we use our second prototype here, we're able to save around 22% the energy. And this is about 11% over what Refine LB was able to save there. However, when we focus on the execution time, we see that Greedy LB is increasing the total execution time. Refine LB is actually reducing it by 17%. But our approach here was not able to really improve the total execution time of the application. And this happens because we have 3 virtual processors per core, and we're only doing migrations inside one socket. So we have like 24 tasks to divide between these 8 cores inside the socket. And this was not enough for this kind of approach to work. So we're focusing on some of these issues for future work. So to try to finish my presentation, so just to come back, the idea of this work is to try to keep the same performance that we have with an application or improve it by doing dynamic load balancing and dynamic voltage and frequency scaling. And so this is going to work when we have these imbalanced applications running on a platform where we can set this kind of frequencies, okay? And for that, we have an energy daemon and a Charm++ module that is currently works with in 2 different prototypes. And what we see in the results is that the first prototype was able to provide some performance improvements for one benchmark between some energy improvements between 4% and 13% when compared to load balancing algorithms. And the second prototype was able to achieve some significant gains in energy, but no performance gains, okay? And for the future work, we are mainly focusing, and Edson is mainly focusing on evolving the hierarchical prototype so we can add some migration between the sockets, okay? So then we can try to improve the performance of the applications. We also want to run more experiments in different platforms and maybe some heterogeneous platforms using, let's say, ARM and Intel to see what happens. And with more applications, because the application is going to affect the kind of results that we have here. And with that, I'm finishing my presentation. Thank you.
Thanks. Any questions? Yeah. It was a long question. Yes.
I can repeat the question if necessary.
So, okay, interesting presentation. I had a couple of questions. The first is, do you both, and I wasn't quite sure from the presentation, do you both increase the frequency on heavily loaded, like go to turbo mode, as well as decrease the frequency on lightly loaded sockets, or are you just doing one or the other?
So when we see that let's say that the load in a socket changes, we can increase back the frequency of that core. Okay.
Okay, but you don't try to for the one
turbo, let's say.
Okay.
And I can bring that to my colleague, and maybe we can see what he's able to do with that.
The reason I ask is I've seen work in the past that has looked at trying to increase the energy efficiency by clipping some of the ones that have try to bumping some of the ones that have gotten behind or things like that. So I was just wondering, is there a published paper on this that?
Not yet.
Okay. And then my last question is, you mentioned on doing this on a socket granularity. Do you have any intuition as if you could do it on a finer grain? For example, if in future generations you could do it on a core or a small chunk of cores, whether that would provide additional efficiency gains?
Yeah. Our initial idea was to work at a core level, right? And that's why we have that kind of first prototype. But then we see that even though we can set in the platform to say I have this different governor for this different core and set different frequencies for the cores inside the same socket, you're still going to run probably at the highest frequency for all cores inside that socket. So we are not able to do that right now, but we sure want to do that. Okay.
Okay. Oh, one more question. Two more.
If we run short on time, I can answer questions later too. I'm going to stay here for the 2 days.
Interesting results. Do you have more? So, are the energy measurements for the whole cluster?
Oh, so
is it like a power meter to the whole thing, kind of thing, or
we are capturing power and energy for the sockets only there.
Using the RAPL interface of Intel processors?
Yeah, for the Intel, I think he uses RAPL inside his energy daemon there.
Okay, maybe it's the energy RAPL library. So you have 20%, not 20, 18% time difference between the last two results you showed for the second prototype. So without your energy load balancer, it was 18% faster, but with your energy load balancer, it was slower but more energy efficient. Do you have more insight on why?
Yes, sure. When we were running, let's say, just a load balancer, it was a centralized load balancer controlling the tasks in all 192 cores. And with that kind of control, we are able to move tasks around and make a better scheduling. And in that scenario there, we had like 24 tasks inside each socket, and the load balancer there was not able to improve much. So we see that there is a lot of imbalance between sockets, right?
No. My question is, why is it, so the idle power is usually high.
Okay.
So why is it more energy efficient even though it's slower? Do you have more insights on that?
Okay, I see. So there's just the really big difference when we decrease the frequency of the sockets that are less loaded. So that's where all the energy savings are coming from. So I cannot give you much more detail right now. Maybe I didn't catch all the things in your question, and we can discuss it later.
We can talk offline. Thank you.
Next question.
I mean, I don't know how technically possible this is, but have you considered to hook this energy daemon into the kernel itself and then say go into a C state on the core instead of just throttling the frequency? Because that presumably would give you much more energy savings.
Yeah, maybe it can be done, but I think he's tried something similar. I cannot be very sure right now. I can ask him, but I think he's tried something similar, because this is not his only work with energy consumption, right? So it's the one that's using Charm++ right now. Okay.
Some of that is not here. Some of these both combinations of options, whether you want to do test or now Apple or generally the industry is more higher level interfaces for specific technology and let the processor decide maybe Robert wants to say something about it, but that's the direction they are going. So
I think we have, okay, last question.
So on the second application where you saved power but it didn't run any faster, that seemed fine to me. You wanted to save power. But on the first application, you went even faster and saved power?
No. Well,
maybe I misunderstood the data.
When we do load balancing and use the energy module together, we are being faster and saving power.
Yeah, so that was on the first example.
Yes.
So how does that work? Because that seems a bit counterintuitive.
Well, we first reschedule the tasks in the parallel platform, which means that we're doing load balancing. But there is still some loading balance that remains there. And we have some sockets that are running a little bit less work than others when we do this kind of load balancing. And then we do DVFS there. And we take that remaining imbalance to do to improve power efficiency. Not the first one. Okay. Oh, thank you.
Okay. Very interesting talk. Thanks, Laercio. Our last speaker is Alex Brooks. He's